Okay, great. Can you hear me? Okay, so if in case anyone missed, I am Dániel Berényi. I'm putting together all this stuff with the help of Máté and Gergely. And usually I'm working in the GPU lab programming, crashing compilers, crashing drivers and everything else. But from time to time I'm doing physics. And in this talk I will be talking a little bit about physics and programming with the topic is this chiral magnetic effect and Wigner functions. Okay, so what is this all about? So we already heard many things about heavy ion collisions. It is not a surprise, our group is related tightly to heavy ion collisions and elliptic physics. And in certain cases, these heavy ions are not in a head-on collision, but they are just near to miss each other and just the very edges are colliding. And in these cases, some crazy things could happen because some strong magnetic fields could form. These nuclei have no electrons, or they are fully ionized, so they have a really big electromagnetic fluctuations going on and creating all these large magnetic fields. But also, when the collision takes place, we have extremely strong QCD fields going on. And as this kinemagnetic effect is about an anomalous current, electric current that appears not in the direction of the collision but perpendicular to this plane, parallel to the magnetic field. This is something that is quite unexpected, and this has intrinsic origins in the theory of strong interaction. We would like to have some model of this process, and what is going on, it is a little bit complicated, but a little bit of explanation is connected to the spins of the particles, quarks that are flowing there, and their momentum and spin. So what is going on? Initially, when the collision happens, we have a quark-gluon plasma form, and all the quarks are freed from the nuclei, and initially they have a neutral distribution in terms of chirality, that is the relation of the direction of spin and momentum when there is a strong magnetic field. But, and here comes the funny part, there is a strong gluonic field that has some strange properties. I'm not going into details, but it could change the chirality of the particles. Now this means that the chirality flips of some particles and the direction of movement will change, and because the different quarks have different charges, this will lead to a charge separation and an electric current. And we'd like to calculate this process because it seems really interesting for experimental people. Okay, so it involves classical electromagnetic fields and involves strong interaction fields, gluonic fields. It's really complicated, but it can be simplified by color diagonalization and other tricks. So we have a quantum electrodynamical problem where fields, the AZ and BZ components that are in the plane of the collision, are coming formally from the strong fields, the QCD fields, and we have BY, which is the classical magnetic field. Okay, so we have an equivalent formulation, but we are now tasked with the solution of a QED system under influence of strong fields, but we have a tool for that, and this is what I would like to talk about. So there is a mathematical tool, so to say, the Wigner function. It is a quantum analog of the classical phase-space distribution function. So let's first discuss this. What is the classical phase space? Everyone can imagine a pendulum. This is the simplest physical system. We have a point fixed, and we, using some rope, we can hang a point mass, and we can kick it, and it will swing. Great. We can record the time series of the position and velocity, and we have nice cosines and sines going on. If we put them together, and now not considering the time axis, but the position and velocity map, we will see the state of the pendulum going in a circle around, and the radius of the circle is given by the energy that we put into the pendulum. So if it is rest and not moving, it is in the origin, and if you have larger and larger energy, it will go in a larger and larger circle until it goes around. Okay, so this is phase space in a classical sense, when we have point masses and that seems like. What is a classical phase space distribution? When we have some uncertainty, for example, in some of the properties in the energy, for example. So this line of movement will spread out. We will end up with some probability distribution over this phase space. Great. Now, the problem is a little bit complicated in quantum physics because we have Heisenberg uncertainty relation. We cannot measure the position and momentum at the same time of a system or a particle. So how to have a phase space there? Because this is what we would like to talk about. So there are some problems going on, and obviously it is different from the classical stuff that we considered before. But if we are sacrificing the strict non-negativity of probability distribution function, we can create something that looks like that in a certain sense and could at the same time describe quantum phenomena. Okay, great. And it is also working because when we project back to only spatial or only momentum space, we can get like a good working probability distribution in the classical sense. So this tool is the Wigner function. It is somehow a tool to deal with quantum systems. And for example, if we take the analog of the pendulum, for example, a simple quantum harmonic oscillator, we can have a nice, similarly looking circular phase space distribution. This is a Wigner function for this one. Okay, so I just inserted this slide because there were people talking about the density matrix. And you can understand the Wigner function, for example, going from the density matrix or coming from straight from the wave function. You can go to center of mass coordinate system, put in some crazy factor involving the electromagnetic fields. This is line integral of the vector potential. And then you can create a Fourier transform with respect to the center of momentum position. Take the expectation value of vacuum, and you are in a real, you are in a single time formalism now. You have position, you have momentum, and you have a distribution over it. Okay, great. So we can try to attack our problem with this. So when we are describing these relativistic quantum systems, it turns out that this form is necessary to ensure the relativistic covariance. We would like to evolve our system when there are strong fields present, and we would like to calculate some meaningful quantities. What is the mass distribution? What is the current distribution? And things like that. And it turns out the Wigner function contains all these information because it has 16 components. Okay. So we are interested in the time evolution. We start with some known state, vacuum. We start with vacuum and push in all these external electric and magnetic fields and evolve our system and try to extract useful information from the end phase space distribution. So without skipping the derivation, we have 16 components of real functions coupled in a large differential equation system. And the operators appearing here, these dt, dx, and p, are in fact operators, differential operators, and moreover differential operator series that are expanded in H bar and containing larger and larger gradients of the external fields, electric and magnetic fields. If you look a little bit closer, until this point, this is the classical equations of motion, but you have corrections to it, okay? Because of all the quantum stuff going on. So this is what we need to put into these equations and operate on all these unknown functions. So it is a really complicated set of differential equations. The initial conditions for vacuum are relatively simple. We have just some energy parameters inside. Okay, so it is something that looks really hard. We have 7 dimensions, 16 components, and really complicated operators acting out. So we usually simplify things. We choose some special field configuration. For example, our electric and magnetic fields have no position independence in some sense, or at least in a restricted form. Set some fields component exactly to 0, so we can cancel out large part of the equation systems. Truncate the differential equation series up to some point, or set mass to 0, and then only 8 components remain. So we would like to choose some of these, or multiple ones of them, to get into a reasonable domain of computability. Just for example, for mass equals 0, here are the 8 components, and it's a little bit easier. Okay, so we would like to solve this, and of course it is impossible to get anything with analytical tools. So we turn to numerics. How to deal with such a complicated differential equation system? What we know that we expect these functions to be analytic, so we don't expect any sudden changes in these functions. So we can choose a basis set that satisfies these properties, infinitely differentiable, and decays to zero when we go to infinity momentum or something else, and we can expand our unknown functions over them. This stuff is going on that we introduce some coefficients that will be multiplying these basis function components, and if we sum them over, we get some good approximation probably for the unknown function. Okay, but this is still something that we cannot handle. When we choose this so-called pseudospectral collocation, for the basis set we have a set of points where we require the error of our approximation and the original function to vanish, so we can get a dense linear algebraic problem, because now our unknown function is discretized and our basis functions are discretized, and now it is just a matrix vector multiplication. Good, so we have dense linear operation. Did someone mention dense linear operations? Okay, these are ideal for GPUs. Element-wise addition, scalar multiplication, tensor multiplication. So these are good for GPUs, and some reductions, of course. But and we can just write a few kernels from them in OpenCL, and we are done. Okay, but let's consider a little bit what kind of expressions could arise in our system. So I just brought here something arbitrary just for illustration. So if we plug in this expansion into this expression where f is the unknown function that we would like to solve for, and g and h are just arbitrary other functions, and the Greek letters are just constants, we get something like this. So when we have multiplication, a scalar multiplication of the unknown function, we have a scalar multiplication of the matrix vector product. Okay, that's great. If there is a differential operator, it only acts on the basis function, so I just need to calculate the derivative matrix of the this matrix, and I'm done. The kernel I need to run is unchanged. Okay, great. When there is a function that is not the unknown function, it is just get discretized and it will be summed over later. Okay, maybe this is a mistake. In this point, it is even the summation is missing. I just discretize it. And if there is an unknown function multiplying the known function and some constant, I get some. So things are getting a little bit complicated because I will have multiple tensors I need to sum over, because one is coming from the discretization of another function here, this g at the xj, and one term is coming from the basis function, and there will be the coefficients. And they are all summed over. Okay, so that they will be summed over. Okay, so in multiple dimensions things are going to change even more, because our coefficients will get more indices and there will be more basis functions, so everything is getting bigger and bigger, and this jz will get a little bit more bigger than it's supposed to be. And so things get a little bit larger, and we have larger and larger tensors and tensor transformations. Okay, so we need to do something with this, because we have this equation system for the Wigner evolution equation that is a little bit, so it is so general, and we always need to specialize from some cases, and what we really would like to play with is the external fields. And if something is zero, it would cancel out really large parts of the equation system, and I don't want to spend time multiplying zeros with really, really big tensors, because it doesn't make any sense. So I don't want to rewrite my solvers and my equations every time I change something, and I would like to do some symbolic simplifications. For this, and we can use some C++ expressions and play around a little bit with them to get something that abstracts over all this stuff. So let's build an expression tree. We already heard a bunch of stories about expression trees. Here we have linear combinations, summations, coordinate multiplications, and differential operators in our expression tree. And at the leaves we have n-dimensional functions, variables, and constants. So this is what we start with, and then these will represent our equations, and we can call the appropriate OpenCL kernels at the different points when we traverse and evaluate the tree. But, as I mentioned, I would like to do some symbolic simplifications. I cannot just plug in Mathematica from Wolfram into the compiler and into the source code to eliminate all the zeros for me, so let's play around with C++ types. Let's start with a trivial structure called null that contains nothing. Okay, it's quite uninteresting, but let's write some operators for that are still uninteresting and does nothing except preserving the type. Okay, so I adding two nulls together, I get null. If I subtracting them, I get still null. I'm multiplying and blah blah blah. If I'm multiplying anything with null, I get null in both directions. If I divide null with something, I get null. Okay, great. How this solves stuff? I have three component vectors all around, and I'm calculating all these cross products of differential operators with cross products of crazy stuff. I would like to simplify zeros out of them. But for that, I need some vector type where I have sometimes constants, sometimes symbolic zeros. Okay, I need a tuple-like stuff for that, so let's introduce a vector which have type arguments for all these three components, so I can set any one of them to zero, symbolic zero. And when I write all the operators for this three vector class, like dot product, cross product, whatever, it would propagate through with this null type that I defined, and I can get out exactly which component was symbolically zero and which one was not. Okay, so at the end, if we put everything together I told you about, we can write some code like this. So I have some components, some scalar values that are coming from my fields. I can introduce some symbolic differential operators in different directions. I can introduce some coordinate variables. I can make a vector of them because, well, my vector is symbolic. I can put everything into it. And I can just write really cross products of symbolic vectors and differential operators. This is the nabla vector constructed from all these three differential operators. I can calculate the cross product. I get back something that when multiplied with functions acts like we expect, differentiating the appropriate components. And I can formulate my Wigner state function that will have all the 8 or 16 components exactly in the same way I did with the 3-component vector, except with more components. And I can really just write down almost in the same way my equations as I would like to, and all the zeros propagate everywhere, kill out all the terms that I don't need, and when I traverse the tree and call the kernel functions, only those will be executed and there is some interesting stuff going on and not just zeros. Okay, for the time stepping, we can use a simple force order Runge-Kutta and evaluate all the right-hand side repeatedly. This is not of interest, and we can write out all the stuff in the file. So at the end, if we get back to physics, we can really calculate what is going on in the real-time formalism. And as I told you, first we switch on these external fields. It is a pulse, basically a heavy ion coefficient. So this is just for a demo field, but the heavy ion results not quite differ from that because it is really robust. So first we get our external fields happening, and they driving an axial current that is a little bit later taking its peak, that creates all this axial charge, so pulling out, creating the chirality imbalance between the particles, and after that, after a certain time, we have our anomalous vector current forming, and then it decays to some constant value when all the dynamics are dying off, and everything is settled to some constant value. Okay, great. How does the Wigner function looks like in phase space? This was a 3-dimensional calculation. I cannot put on a 3-dimensional density because you would see nothing. So this is a 2-dimensional slice of it. It has some nice wavy patterns. This looks like the harmonic oscillator, but the internal structure is a little bit different. And basically how this evolves is started from 0 at the beginning when we are at vacuum, and it starts to oscillate and form some peaks. And if we calculate different projections, we can get all the observables of this in terms of different directions that we are looking at. Different components look a little bit different and have these nice structure. So we really need a high resolution in multiple dimensions because we need to resolve all these fluctuations, because if we miss something it will blow up because the gradients would be truncated and there will be loss in the precision. And if we really get back to series physics, we can get a prediction for different collision energies, how the effect would change. So we would like to predict this pink curve. I hope you see it. This is the anomalous current that experimentals would like to measure at the end, and we see that for higher and higher energies, the external field paths will be shorter and shorter, and they produce lower and lower yield of this anomalous current, and this is consistent with the experiments that all this stuff is vanishing at LHC and larger energies and only relevant at lower energies. Okay, so in summary, I showed you this Wigner function formalism. It could be used for many other stuff, but in this occasion we were talking about this pyromagnetic effect. It is a complicated equation system. It can be attacked with all these tools, and I hope you get something about this nice simplification, because it is really playing well with C++ and all other tools, and it could be used for other cases when you need to cancel out something. And we really needed just a few kernels to write for a given set of dimensions, and so it is computationally tractable at this point. So we have GPU power that could handle these simulations. And the speed up with respect to a single-threaded CPU version, of course, it depends on many factors, but it is around 30, and it is really important when you have calculations running for weeks, for example, as in this case. Okay, so thanks for your attention.
So any questions?
How many xi do you need?
Sorry?
How many xi do you need? How many points?
For the largest grid that fits into memory, not what I would like to have, it is something 256. And it's really needed. Below that, you get some errors because of truncation and things like that. So it is getting serious. So you can live with 128, but it is really better if you can go a little bit up. And this is unfortunately memory limited at the end.